We already talked a little bit about the distribution of speeds in a gas. Now, in section 2 of chapter 20, the book introduces the idea of root mean square. So I'm putting it here even though otherwise we're talking about pressure. So one thing to know is that RMS means root mean square. This is something you're actually going to see in a lot of different contexts. This is not just something we use to calculate velocity in this context. RMS is a general technique, so you might see it in other science classes or math classes or physics in other contexts. So the first thing is to remember the definition of speed. This is a place where we literally mean speed and not just velocity. And so we now have 3 dimensions to worry about, right? Our gas is a 3-dimensional object. So you would have your x component, your y component, and your z component. You would take each of those squared, right? So these are direct component vectors or component magnitudes of your velocity vector. You square each of them, sum them, take the square root. That's your definition of speed. So remember, v without the little vector symbol above it should mean speed, not velocity. So one definition of average speed uses the square root of v squared average. So why is this? Well, think about your molecules that are zooming around in the box. If you just asked what is the average velocity, well, the answer would be 0. Even if you confine them to one dimension, you would imagine that half of them are going to the left and half of them are going to the right. On average, that's 0. But that's their average velocity, not their average speed. So once you want to know the average speed, you have to say, well, what do you mean? And so what we mean is typically this. You've taken this and you've squared it, so that's literally the x component squared plus the y component squared plus the z component squared. And then you've said, well, take the average of that. So that is your RMS. It's the root of the mean squared. So now one thing to think about here is then how does this relate back to individual components? Well, we expect that there's no relationship between x, y, and z, right? That again, these molecules are zooming around in random directions. So what that means is that when you have your average here, that you can think of that as being related to just your average in x, y, and z, right? Approximately. And obviously this would not be true if they were dependent, if somehow y and z related, for instance, but since they're independent, this holds. What this means then is that if you want to relate a single directional component to RMS, which is going to be the quantity we typically talk about, it's just actually 1/3. And again, note the squares. The squares are, you can just square root both sides, that's fine obviously, but we're going to be using this result later. That if I just want to know what the average x component is, again, squaring it, I can say that that's 1/3 of my RMS, since my RMS relates to each of these added, and there's no reason to believe if they're moving around randomly that y or z is, say, bigger than x. They're all equivalent. Okay, so now let's try to calculate pressure. The book does this derivation, and it isn't something that you need to memorize, but it's a really nice way to think through what's going on. I think it's really helpful to understand the macro-micro connection. So we're going to talk through it. So I want to give an overview before we jump in because it's spread out over multiple slides. First, we're going to look at the momentum change of molecules. And remember that momentum change is also an impulse. Impulse allows us to actually think about average force over a time window. And time window is going to relate to density of gas and their speed they're moving. So by doing this, we can actually then relate the area of the wall of our box itself to the force and get pressure from that. And force is going to be then related to these quantities that we know about, such as density and the speed. So first, part of why I like this is it's also a nice basic review of some dynamics and kinematics. If we think about the momentum change as these bounce off the wall, initially it's moving to the right, and we're going to say it's just only moving to the right. It moves to the right, then bounces off the wall, elastically. No energy is lost. And since the wall itself doesn't move, that means that it must come back with the same speed opposite direction. So our change in momentum is final minus initial, and final was negative, initial was positive, so our change in momentum is -2 mvx. So then, if we think about what's happening in time, we say that I'm going to consider a certain time window over which multiple collisions occur, n of them. And we're going to, for right now, kind of say they all have the same speed in x. Now what's actually true is that we're going to take the average. So at some point we're going to switch to saying they all have the same speed to just calling this an average. It's a little bit hand wavy, but it works. So all we've done here is now talked about the total momentum change over a time window and just multiplied by number of collisions. But now remember how impulse was defined. The impulse is defined as the change in momentum, which is an average force multiplied by the time window that it's occurring over. Now, we can talk about, so far, the change in momentum of the gas. So this would be the average force on the gas. But what we actually want is the average force on the wall, but from Newton's third law, that in this case these interactions mean that the average force on the gas is equal in magnitude but opposite in direction to the force on the wall. So we can get the force on the wall by taking the total momentum, dividing by delta t, and switching the direction. Since again, this force in the impulse equation is actually the force on the gas, but we want the force on the wall. But they're interacting, so it's a Newton's third law pair. So okay, we now have some equation for the force on the wall, which divided by area would give us pressure, but this has velocity in it and only the x component and the number of collisions, so we have more work to do. How many collisions are there? Well, imagine part of the volume that has a width given by the x component of velocity times delta t. Every molecule moving to the right that fell in this initial volume, that again, we're kind of thinking about them all having the same speed, would actually hit the wall in that time. So the volume of this is given by the area of the end times the thickness. And the number density is, again, the normal number density, n over v, but only half of them are moving to the right. Half of the molecules you would find in here are actually moving to the left. So that's where the 1/2 comes from. We then multiply the number density by the volume, which was A delta x, but delta x was just given by Vxt. So now we know how many collisions it was. We can go back to our force equation and plug this in. With a little simplification, we're now down to this. The only thing we need to do now is go from my x component of velocity to my RMS velocity, since that's the value we typically talk about. I do this by using the fact that my average x component is going to be related to my RMS component over 3. And again, this was squared initially, so it's VRMS squared over 3. So that's how I can go from x component, which I don't know, to RMS, which is a component we do talk about. Now this was the force on the wall, and what I actually want is pressure, since the pressure on the wall is really the definition of pressure of the gas. So we divide by area, which was in our equation, and so we're left with this. So what's interesting about this is we've now related the pressure of the gas to the velocity that they're moving and the number density. So this shows you that the number density does matter for the pressure, which we would expect, but so does the speed. Now the other thing that's going to come in here in the next sequence of slides is that you remember the ideal gas law. PV equals nRT. Well, here I have P, and here I have V, and here I have N. So what's left must relate to R and T. So that's why this is an interesting result. Again, V is a microscopic quantity, but we see that a lot of the rest of this here is actually the macroscopic ideal gas law. That will allow us to relate the microscopic quantities to some more macroscopic quantities.